Alright guys, so today we are going to start chapter 7, which is going to be on alkenes, structure and reactivity. But in this part, in this chapter, mainly in chapter 7, we will primarily focus on how to name alkenes and the structure of alkenes. Okay, so those are the primary things that we will worry about in this chapter, and then we will also talk about some of the reactivity, okay, that is related to alkenes. Okay, so in this chapter we are going to talk about some of the very fundamental things about alkenes, but in the next chapter we will jump into most of the reactions that alkenes show. Okay, so in this chapter we will understand what are alkenes, and then in the next chapter we will basically talk about most of the very important reactions that alkenes display. Alright, so these are the learning objectives for this chapter. Okay, so basically in this chapter we are going to talk about how alkenes are made industrially, and then we will also talk about calculating degree of unsaturation. I think you already have some understanding about this, right? So I think we are all already comfortable with the degree of unsaturation. Okay, but basically that is what you do to calculate or understand how many double bonds, triple bonds or rings you have in a given formula, right? So we are already somewhat familiar with that. And then we will also talk about naming of alkenes. So that will take a majority of time today, because I mean we already learned how to name alkanes. We learned how to name aromatic alkanes next, and then today we will talk about naming organic compounds when they have a functional group. So it is somewhat different from naming alkane compounds. So this will be like the second half of nomenclature. Okay, so once you learn how to name alkenes, name alkenes, you can basically use the same exact principles that we learned from this chapter to almost every other chemical compound. Okay, so we will talk about nomenclature in a little bit more detail this chapter, but later on we are going to basically briefly mention nomenclature. We will not be detailed when it comes to nomenclature from next chapter onwards. Okay, and then we will talk about stereochemistry, and then we will talk about stability, and then we will also talk about reactions, some of the reactions, okay, especially electrophilic addition reaction, and then a rule called Markovnikov rule. Okay, so we will talk about these things in more detail in this chapter. First of all, okay, alkenes. Okay, so we basically introduced hydrocarbons in a previous chapter, and then I mentioned what are alkenes. Okay, so once again, alkenes fall under hydrocarbons. Alkenes fall under hydrocarbons. Hydrocarbon means organic compounds that only contain carbon and hydrogen, right? So the primary atoms of hydrocarbons are going to be carbon and hydrogen. So alkenes are hydrocarbons, so you only have carbons and hydrogens. But the unique thing about these alkenes is that you are going to see multiple bonds between carbons. Multiple bonds between carbons. In alkenes, we only had single bonds between carbons, right? But in alkenes, you will at least have one carbon-carbon double bond. You will have at least one carbon-carbon double bond. Okay, so that is the unique thing about alkenes. Okay, as compared to alkanes, alkenes usually have at least one carbon-carbon double bond. Okay, carbon-carbon double bond. So that is the important difference between alkanes and alkenes. And also, this is the first time that you guys have encountered with organic chemistry functional groups. Okay, as I mentioned earlier, alkanes do not have a functional group. Okay, but alkenes onwards, we are going to see these functional groups. Okay, functional groups. So basically, for alkenes, the functional group is going to be a carbon-carbon double bond. The functional group is going to be a carbon-carbon double bond. Are we clear? Alright, so in this slide I have a few examples from nature. Okay, so ethylene is the simplest alkene, or some people call it ethene. Okay, ethene or ethylene, both the same thing. Okay, this is the simplest alkene. Why? Because in order to have a carbon-carbon double bond, you should at least have 2 carbons, right? You should at least have 2 carbons. So this molecule has the minimum requirement to be an alkene. So I also have a couple of examples from nature. Okay, so beta carotene is basically a pigment that is found in orange color. Okay, so these are some of the examples. And by the way, alkenes are sometimes called olefins. Okay, alkenes are also known as olefins in nature. All right, so the other important thing about alkenes is that alkenes are highly reactive, or you can say it's a precursor for many other important organic compounds. It's a precursor for many other important organic compounds. Okay, so alkanes did not show many different reactions, right? The only reaction that we talked about in alkanes is the radical reaction with halogens, right? The radical reaction with halogens. But when it comes to alkenes, since alkenes is an important starting material for many different organic compounds, there are so many different reactions for alkenes. Okay, alkenes are more reactive or much more reactive than alkanes, and therefore you can use alkenes as starting materials for many different organic compounds, especially things that are very important in organic chemistry. Okay, so in this slide I have given you some examples for alkenes and some of the organic compounds or functional groups that you can synthesize using alkenes. These include things like alcohols and alkyl halides, and also carbonyl compounds like ketones and aldehydes. Okay, so you can basically make some very important organic functional groups using alkenes. So therefore, reactivity wise, alkenes are extremely important as compared to alkanes. Okay, alkanes did not want to react with anything, but alkenes want to react with many different things. Okay, so we will talk about most of these reactions in the future. Alright, so industrially, alkene is synthesized using a method called thermal cracking. Okay, a method called thermal cracking. Okay, so basically in this method you will basically make simple or small alkenes such as ethylene or propylene using small alkanes like butane. Okay, so you will take a small alkane and then you will provide very high temperatures to those alkanes. In this example, they are providing 900 degrees Celsius, very high temperatures. Okay, and at very high temperatures you can break small alkanes symmetrically. So it is a radical reaction. It is a symmetrical bond cleavage. Okay, so through radical reaction or symmetrical bond breaking, you will produce small alkenes such as ethylene and propylene. Okay, ethylene and propylene. This is somewhat different or difficult reaction to do. Why? Because you need to provide very high temperatures, and then since it's a radical reaction, we have a less control over this reaction. Okay, and if you want some fancy alkenes, this reaction probably will not do that. Okay, so it is limited when it comes to the type of alkenes that you can make. All right, so the next thing that I'm going to talk about is the degree of unsaturation. And I believe that we have some knowledge on this area already. Okay, so we have already talked about degree of unsaturation when we talk about rings or cyclic alkanes, right? So basically, degree of unsaturation, or DOU, is a calculation or something that we do when we have a chemical formula. Okay, so let's say you have a chemical formula called CN or CXHY. Okay, so basically you will know how many carbons you have, how many hydrogens you have, but basically if the alkane, if the hydrocarbon is saturated, not alkane, if the hydrocarbon is saturated, you are supposed to have, let's say you have n number of carbons, you are supposed to have 2n plus 2 number of hydrogens, right? So if you know the number of carbons, you can easily predict the maximum number of hydrogens you can have for that particular amount of carbons, right? So as an example, if you have 5 carbons, what is the maximum number of hydrogens you can have for this hydrocarbon? 12. You can have a maximum of 12 hydrogens. So basically, by using CnH2n plus 2 general formula, we can calculate Hmax, or maximum amount of hydrogens that are present in a saturated hydrocarbon. But alkenes and alkynes, okay, they are not saturated. Saturated means you have the maximum amount of hydrogen. So in other words, no double bonds, no triple bonds, or no rings. Okay, that is what saturated means. Okay, but alkenes are unsaturated. Or in other words, they do not have the maximum number of hydrogens. In fact, one double bond takes a total of 2 hydrogens from the formula. One double bond takes a total of 2 hydrogens from the formula. So for a hydrocarbon, for an alkane, the maximum number of hydrogens you can have for 5 carbons is 12. But if it is an alkene, you will only have 10 hydrogens. You will only have 10 hydrogens, right? Because 2 hydrogens are used to occupy the double bond. 2 hydrogens are removed to occupy the double bond. So basically, every double bond takes up 2 hydrogens. So degree of unsaturation is basically known as the number of multiple bonds or rings that are present in a molecule. So you can basically calculate the degree of unsaturation using a small formula. You might want to write this down in your book, okay? So the equation that I usually use to calculate the degree of unsaturation is Hmax, which is the maximum amount of hydrogens possible for a certain number of carbons, okay, minus H actual amount of hydrogens you have in the formula, divided by 2. So as an example, let's say that we have a chemical formula called C5H10. Okay, so the maximum amount of hydrogens you can have for 5 carbons is 12, and you already actually have 10 hydrogens, okay, divided by 2. So the answer will be 1. Okay, answer will be 1. So for this particular chemical formula C5H10, the degree of unsaturation is equal to 1. This 1 means the chemical formula that has the C5H10, okay, as the chemical formula could have one double bond or one ring. So you can have a structure for this formula that contains one double bond or one ring. Are we clear? All right. So here's another example from your textbook. Okay. So for a chemical formula C6H10. See if you could calculate the degree of unsaturation. C6H10. This is the chemical formula. C6H10. This is your chemical formula. See if you could calculate the degree of unsaturation for C6H10. C6H10. 2. Alright, let's check. So the maximum amount of hydrogens possible for 6 carbons is how much? For 6 carbons? 14. You can have a maximum of 14 hydrogens. But actually, you have how much? 10. You actually have 10. And you divide the whole thing by 2. So the answer is 2. So degree of unsaturation is 2. Which means a molecule with a chemical formula C6H10 could have one of these possibilities. A molecule with the chemical formula C6H10 could have one of these possibilities. It could have two double bonds. That is one possibility, okay? Or it could have two rings. That is also a possibility. It could have two rings. Or it could have one ring and one what? One double bond. Exactly, one ring and one double bond. What will be the fourth possibility?
One double bond, one ring.
Same thing. Huh? Triple bond, well done. Triple bond. So if the degree of unsaturation is 2, it could also mean that it's a triple bond. Okay, it could also mean that it's a triple bond. Okay, so if the degree of unsaturation is 2, you have many possibilities. Okay, and in this slide I have given you a few possibilities, of course. Okay, one example for each possibility, to be honest. Okay, there are many examples for these possibilities. And then for two double bonds, the first molecule 4-methyl-1,3-pentadiene, okay, that is an example for two double bonds, and the second molecule is an example for a ring and a double bond, okay. And then the third one is an example for two rings, okay, and the fourth molecule is an example for one triple bond. All right, so let's see if you could come up with another example for each of these four possibilities. So take a minute and then see if you could come up with another possibility for each one of these examples. See if you could come up with another new example for each of these possibilities. And if you are watching the video, you might want to pause the video now. So on the board I already wrote 3 other examples or structures for C6H10 chemical formula where you can have two double bonds. Okay, all these 3 structures along with the structure that you have on your presentation will have the chemical formula C6H10. And then let's see if we could write a couple of other structures that will have one ring and one double bond. Okay, one ring and one double bond. So right off the bat, what I'm going to do is I'm going to draw, let's say, a cyclopentane ring that is 5 carbons, and then here is the 6th carbon. Okay, and then draw a double bond anywhere. You can put it here, you can put it here. Those are all different. Get it? Those are all different. So you can basically write many different combinations. Okay, so you can draw many different combinations. Here is another different one. Even you can have the double bond outside the ring, right? You can have the double bond outside the ring. So there are so many possibilities. Maybe you can draw a ring with 4 carbons, and then you need 2 more carbons. You can put it in here, or you can put two methyl groups, right? And then double bond, it could be here, outside the ring. It doesn't matter, right? So there are so many possibilities. Do you see? So 2 rings is kind of tricky, but let's do it. So we can have 6 carbons, right? So here's 4 carbons, 5, 6. All right, here's a possibility. That is 2 rings. Okay, that is another example for a 2 ring. And then 1 triple bond. I mean, we can do something like this: 1, 2, 3, 4, 5, 6. There you go. There is 1 triple bond. Okay, you can move the triple bond around and then can have many other examples. Okay, can have many other examples. So similarly, at home you can try to draw some other structures for the same chemical formula C6H10, and then you will realize that there are many other possibilities you can try. Okay, and here is something that we did not discuss in previous situations. Okay, so if you have a halogen in your chemical formula, I mean, halogens are very similar to hydrogens when it comes to bonding. Okay, halogens are very similar to hydrogens when it comes to bonding. Why? Because halogens attach to carbon with a single bond, okay, and then hydrogens attach to carbon with a single bond. So they are both very similar when it comes to bonding, right? They are both very similar when it comes to bonding. So if you have a halogen in your chemical formula, let's say you have a halogen like this one, C5H11Cl. There you go. You have a halogen in your chemical formula. If you have a halogen in your chemical formula, when you are counting the degree of unsaturation, you treat halogens, or you consider halogens as hydrogens. Okay, you basically replace halogens with hydrogens. So the maximum number of hydrogens you can have for 5 carbons is 12, and then actually you have 11 hydrogens and 1 halogen, but we consider the halogen as a hydrogen, so it will be 12 divided by 2, so it will be a 0. So this chemical formula has no double bonds, no rings. This chemical formula has no double bonds or no rings. Okay, so whenever you have a halogen like fluorine, chlorine, bromine, iodine, you basically replace those halogens with hydrogens when calculating the degree of unsaturation. Are we clear? Alright. So the next heteroatom, the next atom that we are going to talk about is oxygen. So oxygen could be there in organic formulas. It is a very common atom in organic compounds. And if you have oxygen in your formula, you basically ignore them. You basically ignore oxygen, okay? You don't do any modifications to the degree of unsaturation calculations, okay? You just basically calculate the maximum amount of hydrogens, subtract the actual amount of hydrogens divided by 2, okay? So don't do anything, just ignore. If you have hydrogens, ignore, don't ignore hydrogens, okay? If you have oxygens, ignore them and calculate the degree of unsaturation as usual. But the tricky atom is actually nitrogen, okay? Tricky atom is actually nitrogen. So whenever you have nitrogens, okay, so subtract the number of nitrogens from number of hydrogens, okay? So if you have one nitrogen, I mean in the example that you have on your lecture note is C5H9N. So you have one nitrogen. So when you have nitrogens, you will take out hydrogens that are equal to nitrogens. Okay, so you have one nitrogen here. So from the 9 hydrogens, remove one hydrogen. So when you are calculating the degree of unsaturation, you will only consider C5H8. C5H8. Okay, so the actual formula is C5H9N, but you have to subtract hydrogens that are going to be equal to the number of nitrogens. Okay, so if you have 2 nitrogens, subtract 2 hydrogens. Okay, and then calculate the degree of unsaturation. For this one, degree of unsaturation will be 12 minus 8 divided by 2, which is 2. Degree of unsaturation is 2. Alright, so here is an example that you could try at home. Okay, of course when I say you can try, you should do it at home. Okay, and I have 3 chemical formulas. Okay, 3 chemical formulas on this work example. Try to do them individually. So basically you will calculate the degree of unsaturation. And then you will try to draw possible structures that matches the chemical formula. Do you want to do one right now? Okay, so let's try A. In class. So draw me possible structures for the chemical formula C4H8. Draw me some possible structures for the formula C4H8. So if you are watching the video, this is the time that you pause your video and try drawing structures that will fit the chemical formula C4H8. Alright, so the first thing that you do is, of course, when you see a formula from today onwards, what is the first thing that you do? You calculate the degree of unsaturation. That is the very first thing you do, regardless of what I am going to ask next. Okay? You see a formula, you calculate what? The degree of unsaturation. Calculate the DOU. Okay? So you have 4 carbons, so you can have a maximum of 10 hydrogens. You already have 8 divided by 2, so the degree of unsaturation is 1. What does this 1 mean? That is the important section. 1 means you can have 1 double bond in your structure, or you can have 1 ring. These are the 2 possibilities. You can have one ring or one double bond, right? So let's start with one ring. Let's start the possibilities with one ring. Most people got the ring part correct, okay? Most people got the ring part correct. And mostly because I think we already learned the cycloalkanes, right? So you have 4 carbons. So the easiest structure that you could do with 4 carbon ring is what? Cyclobutane. Cyclobutane. This is the first one. And then you can write a cyclopropane, but you know it is only 3 carbons, so we need one more carbon. So here's the other carbon. Get it? 4 carbons. 4 carbons. 4 carbons and one ring, which means one unsaturation, right? So fit the formula. And then the other thing is you can write structures with one double bond. One double bond. Okay? So you can have 4 carbons, 1, 2, 3, 4, 4 carbons. Look at me, look at me. Some people are drawing 3 carbons and telling me that it's 4 carbons. No. 1, 2, 3, 4. Every end and a bend is a carbon, okay? 4 carbons, but this is not correct. This does not have an unsaturation, right? We need an unsaturation, so put a double bond somewhere. There is one. Draw the same thing, but this time put the double bond in the middle. Oh, the location is different, right? So draw one more. 3 carbons. Here is the 4th carbon and here is the double bond. So I asked you to draw 3 out of these 5 possibilities, and then few people did that, okay? But others, please write it down. But from now onwards, you get the idea, right? This is how you do it. It is very easy, okay? They are not rocket science. They're extremely easy, but now you know, right? Alright, so let's move on. Let me fix my presentation and then we will move on. Of course, in the next few slides, I have some possibilities for these structures. I mean, you don't want to copy them, okay? It is shameful. You want to do your own thing, right? Alright, so these are some of the answers. If you are watching the video, you can pause and review. Okay, that means you can also pause and review when you go home, okay? So you can pause and review these structures. There are so many possibilities. Alright, so now I'm going to get into the more important part of this lesson, today's lesson, which is nomenclature, naming alkenes. Okay, this is something that you can learn today and then understand it today, and then you don't have to worry about for the rest of your life. Okay, why? Because if you learn how to name alkenes, the theories that you are going to learn today will be applicable to most of the other organic compounds. Okay, are you guys ready? Alright, let's do this. Alright, so before jumping into naming alkenes, I want you to do me a small thing, okay? I'm going to draw an alkane. See if you could name it. Okay? By now, naming alkanes should be very easy, okay? So name this alkane correctly, I will give you a bonus point, okay? So if you are watching the video, you will draw it and then pause the video and try to do this by yourself, okay? Bonus point. So awesome. That's so hard, huh? Alright, here is the structure that I want you to name, okay? And I will give you a bonus point, okay? Oh, I will give a bonus point to the person who's going to volunteer to correctly name the compound on the board. Alright, your time starts now. Alright, there you go. It's the same thing. You will have plenty of chances. Oh, I missed a small structure, like small line. Small mistakes here and there, check again. Small mistakes here and there.
Oh, I don't do this. I don't do this thinking.
Perfect.
I know it's a mistake.
Yay, awesome. Yeah, I'm good, right? You guys know how to do things. There we go. We have received a bonus point.
I'm trying to get there. wait, but if this isn't right, it's not right. This isn't right, so
I was just doing it.
Madison was looking at it. You want me to go?
Yeah, you do. He showed me first. Next one. Yeah, you will get the next one. Yeah, you can see the pages.
Yeah, I was gonna write it. I was just
Right.
The idea is correct.
Yeah.
You have the idea, but you have something because you just like, I don't know.
That's because this one was right.
Yes. Oh, well, one mistake.
All right, good job. Good job. Well done.
I tried.
So let's do this. Let's do this one more time, okay? So let me explain what she did, okay? All right. So basically, first thing that we do when we are naming alkanes, we try to find the longest continuous carbon chain. So the longest continuous carbon chain would be, first of all, identify the junctions, okay? So first junction is right here. So you can go to the left or to the right. Doesn't really matter. So let's go from here. Okay, from here you go up because that is where the long carbon chain is. In this junction, of course, you go to the left. Here is the longest continuous carbon chain. Once you identify the longest continuous carbon chain, you try to name it. So this one is actually, so you number it. Once you identify the longest continuous carbon chain, you number it. So this will be 7 carbons, but you have 2 choices. You can start numbering from this end or this end. Okay, you can start from numbering from the top or the bottom. Where will you start? Bottom. Why?
It's closer to the first.
Perfect. Closest to the substituents, right? So when you have a choice to make when it comes to start numbering the carbon chain, right? You will start from the end closest to the substituent. So this will be number 1, 2, 3, 4, 5, 6, 7. Okay? So this is how you number them. Now you identify your substituents. You have an ethyl group. You have an ethyl group on the 3rd carbon. So this is a 3-ethyl. You have a methyl group on the 2nd carbon. So this is a 2-methyl. And you have another methyl group on the 5th carbon. So this is 5-methyl. 5-methyl. Okay? So overall it is a 7-carbon alkane, so it's a heptane. Okay? So overall this is a heptane. This is a 7-carbon alkane, so it is a heptane. So let's write the whole thing together. So when you are writing the full name, you will arrange your substituents alphabetically, right? Alphabetically. So ethyl comes first. So it is 3-ethyl. And then you have 2 methyl groups, 2 and 5. Since you have 2, you have to use di. Most people forgot the term di, and that is the problem with Abdullah's answer, okay? You forgot the term di. That is where you missed your bonus point, okay? Huh? No. Alright, so you have 2 methyl groups on number 2 and number 5 carbon. So 2,5-dimethyl and heptane. By the way, you also have a dash line between methyl and hexane. Oh, how come it is heptane? So you have a dash, those are wrong, okay? So you only use a dash line between numbers and letters. You use a comma between numbers, and then everything else should be in one sentence, okay? One sentence. There are no spaces or anything like that, okay? So that is how you name it. So you have the idea, right? So you pick the longest continuous carbon chain. You start numbering the longest carbon chain starting from the end closest to a substituent, and then you name your substituents, and then you put everything together according to alphabetical order. Are we clear? Alright, so this is how you name alkanes. But let's see how to name alkenes. Let's take a look at the rules that governs the nomenclature of alkenes. Alright, so the most important thing about, or the difference between alkenes and alkanes is that starting from alkenes, we introduce something called a functional group. Functional group. An atom or a group of atoms that basically behave similarly during reactions, okay? So we call them functional groups. So alkene functional group is a carbon-carbon double bond. So for this functional group, you have two carbons involved, right? So whenever you have a molecule, an alkene, whenever you have an alkene, okay, let's say this one, whenever you have an alkene, the most important thing to do is to include the two carbons, that share the carbon-carbon double bond into the parent carbon chain. Okay, so when you are figuring out the parent, you should always include both these carbons in your parent chain. That is the most important rule. Okay, so the most important modification that we will learn today is to include both carbons of the double bond into the parent chain. So look at the example at the bottom in your lecture note. Okay, so basically, on the top, the first example that you have on the top. Okay, so there are two, it is the same molecule, okay, same structure in the left and right. So you can pick two different parents for this particular structure. The method that is used in magenta color and the method that is used in green color. Okay, but only one is correct, of course. You can't have two different parents and have the same structure, right? Only one is correct. And in these two cases, the magenta example is correct. Why? Because in the magenta example, as you can see, both carbons are included. Both carbon-carbon double bond carbons, or both carbons that have the double bond is included in the parent chain. But in the green method, only one of the carbon-carbon double bonds are included. Get it? So in the green method, of course, it has the longer chain, but it only includes one carbon. So when it comes to alkenes, it is not the longest chain that is most important. It is including both carbons of the carbon-carbon double bond that is important. Okay? So in the magenta method, even though your compound has less number of carbons in the parent chain, it includes both double bonded carbons, right? So that is the correct method. So that is the most important rule that you will learn in this chapter. Okay, in this chapter, include both carbons. Okay, not just one carbon. And then you have to number the chain. Now we have to number the chain. When you are numbering the chain, in alkanes you always try to give a lower number, or try to give the lowest possible numbers to your substituents, right? But now we have someone more important. We call it the carbon-carbon double bond, or the functional group. Starting from alkenes, substituents are not the most important parts in our molecule. It's the functional group. Okay? So therefore, when numbering the parent chain, you always prioritize the functional group. Okay? So the second most important rule is that try to give the lowest possible numbers to your functional group. Okay? So the second rule is provide or give lowest possible numbers to the function. That is the second most important thing. Okay, so first thing is, of course, include both carbons into the parent chain, and the second thing is, when you are numbering the parent chain, okay, you will start from the end. That is closest to your functional group. So here is my molecule. Okay, I have two different chalks. Okay, so basically what I'm trying to do is I'm going to name. This is my parent chain, of course, if you are confused. Okay, so this is the longest chain that includes both carbons of the alkene. Okay, both double bonded carbons, right? So here is my parent, and then I can start numbering from this end. So I'm going to use my purple color, and then I'm going to start numbering from this end. 1, 2, 3, 4, 5. Okay, or someone might think that okay, I can start numbering from this end. 1, 2, 3, 4, 5. Okay, so which method do you think is correct? Purple method or blue method? Purple method is correct. Why? Because if you number the parent chain according to the purple method, starting from the left side, your functional group is first found on the second carbon, right? Your functional group is found between second and third carbon. Okay, but if you use the blue method, your functional group is going to sit between third and fourth carbon. So of course the purple method is better because it gives a lower number to your functional group. Okay, so when you are numbering your parent chain, you should try to start from the end. When you start, you try to number from the end that is closest to your functional group, not the substituent. Okay, not the substituent. But so this is correct. Okay, this is correct. And then you will worry about the substituent. So you have a substituent on the third carbon. Get it? So that is how you do it. Okay, so in this compound you have a methyl group on third carbon. So it's a 3-methyl. 3-methyl. Okay, so then you worry about substituents. I never worried about the substituent until I figure out the location of the carbon-carbon double bond, which is my functional group. Okay, and here's the thing, if the location of the double bond does not matter, okay, let's say regardless of whether you start from left or right, you are still going to get the same numbers for your double bond, then you will worry about the location of your substituent. Okay, if the double bond does not matter, then you will worry about the substituent location. Okay, so substituent location is now secondary to us. Primary thing is the functional group. Are we clear? All right. Have you seen my clicker, guys? Okay. So once you do that, now you try to write the full name. How do you write the full name? First you write the substituent names in alphabetical order, and then you write the name of the parent chain. So when you are writing the name of the parent chain, in this compound right here on the board, it has 5 carbons, so it's pent. 5 carbon means it's pent. Okay, pent. But it is not pentane. Okay, it is not pentane. Since you have an alkene, it is ene. Okay, so the first modification that you need to know when you are writing the alkene name is that the name will always end with ene. Only one letter difference, but it makes a huge difference. Okay, only one letter difference. So this is a pentene, not pentane. Pentene. This part is important. Alkenes will always end with ene at the end. Okay, that is the parent name. But here's the thing. Now this is not just pentene. We have to identify where the double bond is, right? So the double bond is between number 2 and number 3 carbon. Okay, so you will only use the first carbon, okay, which is number 2. So this is 2-pentene. This is 2-pentene. Everyone knows that if it is 2-pentene, the double bond is between the number 2 carbon and number 3 carbon. Okay, you don't have to write both carbons. Okay, you will only use the first number. Okay, and then you have one substituent which is a methyl group on the third carbon. So it will be a 3-methyl. 3-methyl 2-pentene. Okay, that is the name. Alright, so what I'm going to do now is I'm going to give you a few examples on the boards. Okay, do you want to do one more on the board and then try? I think you guys are ready, right? Okay. Okay, so let me write down a few examples on the board and then you will volunteer to write names on the board, okay? All right, so I'm going to pause the video now and then we will start the exercise, okay?
Right over there, dog.
Which one did you do? This one?
I haven't done any of them.
Smile for the camera.
Smile away.
All right.
The purest one.
So you said, what'd you say about getting completely right? You get what?
One bonus.
So when you don't get completely right.
All or nothing, baby.
Now come on guys, we are working for a bonus point now.
Are you allowed to converse together? I think they're cheating over there.
Oh no, they're not doing
We are not. We're just talking about genetics.
Do it independently. Don't talk. Do not talk. Do not copy from each other.
Dr. G, you have the Asian one there? Asian, you have the Asian one? I'm gonna do it. Right.
So this is the extra one, okay? This is not for a bonus point, okay?
I can't remember. I can't remember.
Hey, bonus point is online, okay? Don't mess it up. Double check and don't ask me, okay? Don't ask me. Hey, what are you guys doing? Okay. Don't talk.
You literally told on me, now you're sitting there talking.
Alright, so who did number 5? Who did number 5? Alright, Gabby. So, you picked the chain, parent chain, and you made sure to include the double bond. Okay, that is the most important thing. Okay, even though this is not the longest chain, this is the longest chain with the double bond. Okay, so some people are like, okay, maybe this is the longest chain, so let me do that. No, even though it has more carbons, it does not have both carbons of the double bond, right? So this chain is shorter, but it has both carbons of the double bond. So you pick the correct parent and you started numbering from the end closest to the double bond, and you have two substituents, an ethyl group on second carbon, methyl group on third carbon. So you put them alphabetically, so it is 2 ethyl, 3 methyl, 1 butene. Everything is perfectly correct. Well done, well done. Who did number 7? Madison, let's see. So you pick the longest chain that includes both carbons of the double bond. You did it correctly, so your parent is correct. So you have two substituents. You have a methyl group on the fourth carbon and you have a isopropyl group on the third carbon. Okay, so you put them alphabetically, so isopropyl comes before methyl. Okay, so you did everything correctly and it is a 2-hexene. Well done, perfect. That's a bonus point right there. Okay, who did number 6? Number 6. Right, medicine. Let's see. So you pick the longest chain that include both carbons of the carbon-carbon double bond, which is correct, and you started numbering from the end closest to the double bond, that is also correct, and you only have one substituent, which is a 3-ethyl group. So your name will be 3-ethyl 2-pentene. Well done. Good job. Good job. So let's go to the other board, and I'm going to pause the video now because you can't see those structures.